this video, I'll introduce symmetrical components basics. So part one, I'll just talk about some basics on symmetrical components. And in part two, I'll do some examples to show how to use them, to use symmetrical components to perform calculations on a balanced system, positive, negative sequence, and also on unbalanced system where you have an open phase in a three-phase system. Symmetrical components are very important, and some people refer to them as the language of protection engineers. So it's really important to understand symmetrical components. So let's just start with some basic definitions. So basically symmetrical components, assuming, so there is an assumption here, assuming that the power system is balanced from basically from generation to the point of imbalance or the point of fault. So basically wherever the point where you have imbalance, like single phase loading, or you have fault currents like line to ground, line to line, or line to ground faults that can cause basically the system not to be symmetrical. So with that assumption in mind, any unbalanced three-phase system of phasors can be expressed in three balanced phasors which are called symmetrical components. These balanced systems are positive, negative, and zero sequence components. So this can apply to voltage, current, impedance, resistance, reactance, and so on and so forth. This method was developed by Charles Fortescue in 1918 when he was investigating some imbalance on induction motors. And this, so the method of symmetrical components is used extensively in protection. So some conventions: all phasors rotate counterclockwise at the system frequency, and they are 120 degrees apart. Symmetrical component quantities are phasor quantities. All phasor quantities are phase to neutral or line to ground. And again, the counterclockwise rotation is a convention. You can do clockwise, but you have to be consistent throughout the system. But I think universally counterclockwise is the norm. So for positive sequence components, basically you have three equal phasors. And when we say equal, we mean equal in amplitude and angle, which means they're separated, so separated by 120 degrees. Because it's a full circle, so it's 360 divided by 320 degrees. So in positive sequence, components are usually represented by a subscript either 1 or the plus sign. So if you look at phase A, so the positive sequence of this current, I'm just using current as an example, you can do voltage or anything else. So IA1 as a reference, then IB1 is 120 degrees away from it, and the same thing for IC1, and so on and so forth. And I'm assuming counterclockwise rotation. So negative sequence component, again, three equal phasors, equal in amplitude and they're separated by the same angle, which is 120 degrees. Usually they're represented by the subscript 2 or negative to indicate it's a negative sequence. So IA2 and IC2 is 120 degrees away, and IB2 is 120 degrees. So, and again, it's the same convention, counterclockwise rotation. So if you notice here, if we draw a line here, like a virtual line, as the phasors rotate counterclockwise in this direction, basically, phase A will cross this line first, followed by B, C. So in this case, I'm assuming ABC positive sequence. By the same convention, if I draw a line here and the phasors rotate, I will see A cross this line first, then C, then B. So it's ACB, so it's reverse, so it's a negative sequence. So for zero sequence components, 3 equal phasors, again, equal in amplitude or magnitude, and there's no phase shift. The phase shift is 0 degrees. I drew them here in parallel, but really think about it, just basically it's one phasor without any phase shift, or in other words, IA0 is equal to IB0 equal to AC0. So there's no phase shift in zero sequence. So let's introduce operator A. So this is used when we talk about symmetrical components. So this operator A is equal to, basically it has a magnitude of 1 and an angle of 120 degrees. If you multiply a phasor by this operator A, it will rotate that phasor by 120 degrees counterclockwise. So if you have, say, phasor A, so this is 0 degrees, or the reference, it will not change the magnitude of, so if I multiply that A, phasor A, by operator A, basically it will rotate it by 120 degrees. Because the convention is counterclockwise rotation. Negative A rotates a phasor by negative 60 degrees. Because basically you have so you would have kind of like operator A times phasor A, and minus A times phasor A will be 180 degrees in the other direction. So if you draw the phasors, you will notice that it's minus 60 degrees. And A squared, so it's basically operator A times itself. In algebra, basically 1 times 1, and the angles, they just add up if you are multiplying. So, and 1 times 1 is just 1. 120 plus 120 is 240. And if I add negative 360, because I'm not doing anything, it's a full circle, I get 1. So basically it's 1 magnitude 1 angle of 240 degrees is the same as 1 with an angle of minus 120 degrees. like I said, minus 360 degrees is the same as 0 degrees because it's a full circle. Because you have minus 360 if you go, which is also 0 degrees. So then if you add minus 360 degrees plus 240 degrees, the same as minus 120 degrees. And notice a squared plus a plus 1 is 0. Basically, if you carry out this simple algebra, you will find that it's equal to 0. So as we know, three-phase systems, they have, say, if we call them ABC, because you can call them anything, 1, 2, 3, red, yellow, blue, whatever. So if I call them ABC, so when writing symmetrical components, you write them for each phase. So basically, for phase A, you write positive sequence, negative sequence, and 0 sequence. Phase B, you do the same thing. Phase C, you do the same thing, and so positive, negative, and 0 sequence. So these were symmetrical components for phase current. You can do the same thing for voltage, so impedance and so on and so forth. So symmetrical components exist as a set. This is important to remember. For instance, IA1, IB1, and IC1 will always exist as a set of 3, basically. They will never exist as a pair or alone. So you can't have, for instance, IA1 and IB1 without AC1. You can't. They always exist as a set of 3. Since symmetrical components are a set of 3 equal phasors, they're equal in magnitude and separated by the same angle, which is 120 degrees, typically you only use phase A as a reference. You don't write them for all phases. So you can just do phase A. You can do the calculation in terms of phase A. Then you can use the relationship between phase A to B and A to C and so on and so forth to get the results for the other phases, and I'll show how you do that. And just keep in mind, if you're reading a textbook, or typically you might see like 0 sequence current, for instance, positive sequence current, negative sequence current. But keep in mind, typically the subscript A is dropped. But just keep in mind that these are the symmetrical components of phase A. But if you want to use another phase, it's better to write it out. Say, instead of A, I want to write the symmetric components for phase B. So then it's better if you write AB0, AB1, AB2 instead of I0, I1, I2, because it will cause confusion. Because universally, when people see I0, I1, I2, they imply they are symmetrical components of phase A. So keep that in mind. So in general, you can write the current of phase A is equal to the positive sequence current of phase A plus the negative sequence current of A plus the 0 sequence current of A. engineers are typically lazy. They don't like too many subscripts. They will just drop the subscript A. Then you just see I1, I2, I0. But just keep in mind, I1, I2, I0, it's really with respect to phase A. So if you don't see it, assume phase A. So then I'm just rewriting it in another word, in a different way. So the same thing is just 1 times I0, which is just I0 plus 1 times I1 plus 1 times I2, because I want to display such that I can use matrix format later. So you do the same thing for IB. So IB is just IB1 plus IB2 plus IB0. And what is IB1 in terms of phase A? So here is the positive sequence components. So IB1, if I look at it here, is equal to IA1 with the angle of minus 120 degrees, which is the same as IA1 240 degrees, which is IA1 times 1 with an angle of 240 degrees. And what is this from previous slides? It's the operator A squared. So that's what I wrote here. And IA1 is just I1. So if you do the same thing for IB2, you're going to notice that it's operator A times I2. IB0 is equal to I0. So then I just separated these into, so I just highlighted in different colors. 1 times I0 plus A squared times I1 plus A times I2. So if I do the same thing for the C phase, so I get these three results here. So then I can write this in a matrix format. So the vector of currents, so IA, IB, IC is equal to the vector of sequence currents, because you see here I have I0, I1, I2. So I wrote them here. Then so I take this as a column and I place it here. Then I take this column here and I place it here. Then I take the third column and I put it here. So I wrote it basically in a matrix format. So basically this is here is ABC current or phase currents is equal to, so basically I call this matrix here matrix A, and these currents here are the sequence current, the zero, positive, and negative sequence. And if you want the sequence currents, it's the inverse of matrix A times the phase currents. So matrix A is 1, 1, 1, 1, A squared A, 1, A squared. And the inverse of A matrix is 1 over 3 times this matrix here, 1, 1, 1, 1, A squared, 1, A squared, A. In IBC, basically the vector of phase currents is just current A, current B, current C, and I0, 1, 2 is I0, I1, I2. So from this matrix format here, I know I0 is equal to 1 over 3 times the sum of the phase currents, Or you just multiply both sides by 3. 3I0 is equal to current A plus current in phase B plus current in phase C. So notice, if there is a neutral, like if you have a transformer that's connected as a Y, say like bushing X1, X2, X3, and you have a neutral that's connected to, so bushing X0, and it's grounded. What is the sum of these currents? Is the current that would flow in the neutral, basically, if it's grounded, which is 3 times I0. So anytime you have a grounded Y transformer, this neutral here will see 3 times the sequence current. If there is unbalance or unbalance due to single phase loading or line to ground fault or line to ground fault, basically anytime you have either unbalance like single phase loading or you have a ground fault. So that's the current that would flow through the neutral. So that's important to remember. And then you can write I1, I2 basically. So this is just kind of a quick summary. So typically subscript A, phase A, is usually dropped, but just keep in mind that zero sequence, positive, negative, they refer to phase A. So phase currents is equal to, or this is a vector basically, is equal to matrix A times the vector of sequence currents. So you see here I showed phase A because those are with respect to phase A. Then if you want the sequence currents, that's the equation. But if in this equation here, I'm just dropping phase A basically, or the subscript A. Just so you know that these are, they are the same. So if you don't see A, the subscript A, just keep in mind that they refer to phase A. Then the current that would, or the phase A current in terms of the positive negative sequence and zero sequence is this. So this you see I'm showing A. Here I'm dropping the subscript A, but it's important to remember that. So the same thing for B and C, and A is just a matrix that I showed previously here. So you can do the same thing for voltage. Basically, it's the same matrix. So like we did for the zero sequence current. So V0 is, or the zero sequence voltage is 1/3 times the sum of the phase voltages. So if you have a grounded Y, so the voltage basically from here to the neutral, from here to the neutral, from here to the neutral, that's this sum here. Or if we multiply both sides by 3, you get 3V0 is equal to the line to neutral voltage across, phase A plus phase B plus phase C. So for balanced three-phase system, this will be 0. That V0, the zero sequence voltage will be 0. Otherwise, line to neutral voltages may have a zero sequence component. Line to line voltages never have a zero sequence component because if you do KVL, their sum will always be 0. So in general, if you have a vector of phase quantities, it will be equal to matrix A as defined in previous slides times the vector of the sequence components. Then this vector of the sequence components is equal to the inverse of matrix A times the vector of phase quantities. X is a vector of, it can be voltage, current, and so on and so forth. A is just a matrix of transformation. Thank you and have a great day. And in the next video, I'll give examples how to use symmetrical components.